just as we can write an electron configuration for an atom, we can write an electron configuration for an ion. Metals lose electrons to form noble gas configurations. So when I look at a sodium atom, 1s2, 2s2, 2p6, 3s1, how I get this plus charge right there is it must have lost an electron. Electrons are lost from the outermost to the innermost, and so the outermost will have the highest number. So this is my highest number right here. So this is the one that is going to get lost. So some other atom is going to pull it off the sodium, and I'm going to be left with an Na+. Let's look at some nonmetals. So nonmetals gain electrons to form noble gases. So nonmetals gain electrons to form noble gas configurations. So that means that they'll have a configuration just like a noble gas. So let's look at F minus. So normal fluorine, 1s2, 2s2, 2p5, and it says it's a minus. So that means that one electron comes in, and we change this to p6. Let's look at oxygen. So oxygen is 1s2, 2s2, 2p4, and that minus 2 means that 2 electrons come in. So we change this 4 to a 6. Now notice all these electron configurations. Notice they're all the same. That is called isoelectronic. So we have sodium losing electron, fluorine gaining electron, and oxygen gaining 2 electrons, and they all end up with the same electron configuration as neon. So neon is 1s2, 2s2, 2p6. Now, just because their electron configuration matches neon does not mean that they are neon. They are still sodium, fluorine, and oxygen. So we haven't touched their protons. Their protons, they are the same. So I just have sodium minus 1 electron, and I have fluorine that has gained 1 electron, and oxygen that has gained 2. But they're still sodium, fluorine, and oxygen. So again, for ions, you always lose the outermost electrons, or if you're gaining electrons, you gain electrons to fill a sublevel. So we just did this one, 1s2, 2s2, 2p6. That would give me the +1 charge, so I just leave 1 electron off. And my ion, 1s2, 2s2, 2p6. So an electron has come in, and we just add it to the highest sublevel. So typically they fill a sublevel. So fluorine just needs 1 more electron before it has a filled sublevel. And taking an electron from, say, a sodium atom would give it that full configuration. Now, transition metals are a little bit different. So let's look at a transition metal. Let's find the outermost electron. So I'm going to look at the number that comes in front, and I have a whole bunch of 3s, but I have a 4 that trumps them all. So that is the one that is the highest energy level. So when you look at the transition metals, I'm going to lose these s electrons first. And then if I need to pull off any more, I can lose it from the Ds. And so this is exactly what happens. So I have vanadium +3, so that means it lost 3 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, and then I will have 3d2. So that's my leftover. So those s electrons are lost first. Whenever you have a transition metal, and then you lose your d electrons. So again, S is lost first because that will be always higher than your D, and then you can lose your D electrons. So because of this pattern of how electrons are lost, this is why transition metals have multiple oxidation numbers. So they can lose those S electrons. Usually they lose them together, but then they can lose the D electrons one at a time. So vanadium can have a +2 oxidation number, a +3, a +4, a +5, and then it stops because it's lost its S's and its D's electrons. So just to review about the family oxidation numbers. So when you look at the first family, your alkali metal family, this has one outer electron, and so when it loses it, it gets a +1 charge, so its oxidation number is +1. That's what its ion charge would be. And then your alkaline earth metals, so that has a +2. And then doing the main group elements going over to the boron family, we have +3, carbon family +4, nitrogen family +3, oxygen family +2. The halogens are -1. And then our noble gases don't form compounds typically. Your transition metals have various ones, but I do want you to know this series. So um, aluminum is a +3, zinc is a +2, and silver is a +1. So you should know those. Those are very common metal atoms that they use on the AP test. So ion size. So when electrons are lost, the cation gets smaller. And the reason for this is that the nuclear charge stays the same. So the nuclear charge is just the number of protons. So the nuclear charge is the same, but what is different is the number of electrons. So this lithium atom has 3 electrons, but the lithium plus only has 2 electrons, but both have 3 protons. So when you look at why the size gets smaller, it's because there's less electrons to pull in. And the nuclear charge being the same, it will pull in 2 electrons in tighter than it would 3 electrons. When we look at cations, it is the opposite. So when we add an electron, again, the nuclear charge stays the same. So for fluorine, I have 9 protons, and the ion, I also have 9 protons. This one has 9 electrons, but this one has 10 electrons. So because there are more electrons, the nucleus of the ion can't pull as hard, and so you are going to get the anion to expand a little bit. You also get what is called electron-electron repulsion. So there's more electrons there and they repel each other, and that also causes the electron cloud to spread out. This all has to do with Coulomb's law. So Coulomb's law, electrons repel other electrons, so that means like charges repel. And also the electrons are attracted to the proton, and distance is important. So the closer the electrons are to the nucleus, then the tighter the holds that it will have. This is exactly what we saw in the PES diagrams with that 1s orbital, that the nucleus pulled the 1s orbital in the tightest. So that always took the most energy to remove. So let's look at the trend for atom size. So size increases as you go down a family, and this is because you're adding more energy levels. And when you get to the very, very large atoms here at the bottom, you also get what's called shielding effect. It just means that the nuclear pull can't get through the inner core electrons to reach those outer valence electrons. And so as a result, it's easier to pull those valence electrons off. We have, though, our atom getting larger as we go down a family, and that is because we're adding an energy level with each row. As we go across a row, we have our size decreasing, so it gets smaller and smaller as we go across the period. And that is because we are adding a proton as we go across, but it's at the same energy level. So our nuclear charge increases and increases and increases, and that's going to pull those electrons that are right there in that shell closer to the nucleus because the nuclear pull is greater. You can memorize this atom size by just memorizing what's the smallest and what's the largest. So your smallest atom is helium, so let's put an S for small, and the largest atom is francium down here. So let's put an L for that. So as you go towards francium, it gets bigger, and that as you go towards helium, it gets smaller. But you can't explain atom size just by the trend. You need to go in and talk about nuclear charge and the number of electrons, and also Coulomb's law. So as I go across the period, it gets smaller and smaller because the nuclear charge increases. And because my nuclear charge is increasing, that's going to pull in the electron cloud tighter. And so my size will decrease. As I go down a family, I'm increasing the energy level or the energy shell, and that is causing the atom to get bigger, and there's more electrons.